Hello students, in the last class we have studied the theorem number 14, theorem number 15 and also we have solved some examples based on those two theorems. We will revise those theorems first of all. In the theorem number 14, we have studied that a bounded function f having a finite number of points of discontinuity in the closed interval a to b is integrable on the closed interval a to b. Means if f is a bounded function which has only a finite number of points of discontinuity on the closed interval a to b, then also the function f is integrable on the closed interval a to b. Then in the theorem number 15, we have studied that a bounded function f is integrable on closed interval a to b if the set of its points of discontinuity has only a finite number of limit points, which means that even though a bounded function f has infinite points of discontinuity on the closed interval a to b, then also it can be integrable on the closed interval a to b, provided that the infinite points of discontinuity have only a finite number of limit points. So that was the theorem number 15. Then we have solved some examples based on those theorems. Now in this class we are going to study the next article, integration and differentiation, that is primitive. And in this article we are going to study the theorem number 16. Then we are going to state one important note based on that. Then we will define the primitive and at the end we will state some important remarks. So let us begin with this new article. So the next article is integration and differentiation, the primitive. We firstly show that integration and differentiation are inverse operations. So in this theorem number 16, we are going to show that integration and differentiation are inverse operations. So we will go for this theorem. Statement of the theorem number 16 is, if a function small f is bounded and integrable on the closed interval a to b, then the function capital F, which is defined as capital F of x, is equal to the integration from a to x small f of t dt, where a is less than equal to x is less than equal to b, is continuous on the closed interval a to b, and furthermore, if the function small f is continuous at a point c of closed interval a to b, then the function capital F is derivable at the point c, and we have capital F dash of c is equal to the small f of c. Now we will prove this theorem, theorem number 16. So proof of this theorem is, let small f be a function bounded and integrable on the closed interval a to b. Now as function small f is bounded, therefore by the definition there exists a number k greater than 0 such that mod of f of x is less than equal to k for all x belongs to closed interval a to b. Next, now if x1 and x2 are any two points of the closed interval a to b such that a is less than equal to x1 is less than equal to x2 is less than equal to b, then by definition of the function capital F, we have capital F at point x1 is equal to the integration from a to x1 small f of t dt, and also we have capital F at point x2 is equal to the integration from a to x2 small f of t dt. Now we have mod of capital F of x2 minus capital F of x1 is equal to the mod of integration from a to x2 small f of t dt minus integration from a to x1 small f of t dt, which is equal to the integration from x1 to x2 f of t dt. As we know that x1 is less than equal to x2, therefore integration from a to x2 f of t dt minus integration from a to x1 f of t dt will be equal to the integration from x1 to x2 f of t dt. Now this modulus is less than equal to the k into x2 minus x1, and this is by the deduction number 3. By the deduction number 3, we know that if the function f is bounded by the k, then mod of integration from x1 to x2 f of t dt is less than equal to k into x2 minus x1. Therefore, for a given epsilon greater than 0, we have mod of capital F of x2 minus capital F of x1 is less than epsilon if mod of x2 minus x1 is less than epsilon by k. Therefore, the function capital F is continuous on the closed interval a to b. Next, now let the function small f is continuous at the point C of the closed interval a to b. Let C be any point of the closed interval a to b, and we are supposing that the function small f is continuous at the point C. Then use the definition of the continuity. Then by the epsilon delta definition of continuity, we have for any epsilon greater than 0, there exists a delta greater than 0 such that modulus of f of x minus f of c is less than epsilon for mod of x minus c is less than delta. Next, now we will choose 2 points S and T such that S lies between c minus delta to c and T lies between c to c plus delta. So, let c minus delta is less than S is less than equal to c is less than equal to T is less than c plus delta. Then we have modulus of capital F of T minus capital F of S divided by T minus S minus small f of c. This will be equal to the modulus of 1 upon T minus S integration from S to T small f of x minus small f of c dx. Again, this modulus is less than equal to the 1 upon T minus S into integration from S to T mod of f of x minus f of c dx, and this is by using the theorem number 10. In theorem number 10, we have proved that modulus of integration a to b f of x dx is less than equal to the integration a to b mod f of x dx. So that we have used here. Now this quantity is less than epsilon, which means that the modulus of capital F of T minus capital F of S upon T minus S minus f of c, this quantity is less than epsilon. As this difference is less than epsilon, which means that as x tends to c, then this quantity is equal to the f of c. So therefore, this implies that limit as x tends to c, capital F of T minus capital F of S upon T minus S is equal to the small f of c. But if you observe the left hand side, then the left hand side is nothing but it is the derivative of the function capital F at the point C. So therefore, we got capital F dash of C is equal to the small f of c, and hence the continuity of the function small f at any point of the closed interval a to b implies derivability of the function capital F at that point. So in this way we have proved this theorem number 16. Next are two notes based on this theorem. Number first, as C is any point of the closed interval a to b, therefore we have for all x belongs to the closed interval a to b, capital F dash of t is equal to small f of t, and which implies that capital F dash is equal to small f, which means that the continuity of the function small f on the closed interval a to b implies the derivability of the function capital F on closed interval a to b. And number second note is, above theorem is sometimes referred as the first fundamental theorem of integral calculus. So theorem number 16 is sometimes called as the first fundamental theorem of integral calculus. Next is the definition of primitive of a function. A derivable function capital F, if it exists such that its a derivative capital F dash is equal to a given function small f, then that function capital F is called a primitive of small f. See here how we have defined the primitive of a function. If capital F is a derivable function such that its a derivative capital F dash is equal to the function small f, then that function capital F is called the primitive of the function small f. Next one is one important remark based on the above theorem number 16. That remark is, the above theorem 16 shows that a sufficient condition for a function to have a primitive is that it is continuous. Theorem number 16 tells us that a sufficient condition for a function to have a primitive is that it is continuous. Therefore, every continuous function small f possesses a primitive capital F, where capital F is defined by the equation capital F of x is equal to the integration from a to x f of t dt. Next one. However, continuity of a function is not a necessary condition for the existence of a primitive. What does this mean? This means that the continuity of a function is only a sufficient condition for a function to have a primitive, but however, it is not a necessary condition for the existence of the primitive, which means that the functions possessing primitives are not necessarily continuous. Means there are some functions which has primitive but they are not continuous. So like such is the remark based on this. So in the today's class we have studied theorem number 16, we have studied the definition of primitive of a function, and also we have discussed some important notes and remarks based on the theorem number 16 and the definition of the primitive. We'll stop here and we'll continue in the next class. Thank you.